Welcome to this talk with the title Long-Term Stable 120 Watt Fiber CPA with 1.3 gigawatt peak power at 2 micrometer central wavelengths. Ultrafast lasers find many uses in industry, biomedical, and fundamental research applications. The most demanding applications require extremely high intensities, which can be reached with ultrafast systems that emit energetic pulses with excellent spatial beam quality that allows for tight focusing. Simultaneously, a high pulse repetition frequency is often desired for short acquisition times and high contrast measurements. Now, these demanding parameters are currently mainly provided by lasers with an emission wavelength at or around 1 micrometer. So the emission wavelength, in turn, is one of the keys to many new applications, since it's one of the central aspects on the nature of light-matter interactions. There are currently two main strategies for achieving sufficient performance in the different wavelength regimes. The first are large-scale facilities like synchrotrons, which are expensive and quite limited in accessibility. The second is laser-driven nonlinear frequency conversion, with prominent examples being difference frequency generation or high harmonic generation. Now, it is known that these conversion schemes can benefit from ultrafast lasers with longer wavelengths, which constitutes a very strong demand for their power scaling and the availability of commercial turnkey systems. Now, answering this demand is the goal for our company, Active Fiber Systems, to develop longer wavelength systems. Now, besides the high power systems at around 1 micrometer wavelengths that Active Fiber Systems has traditionally built, we have now started to develop high power lasers at 2 micrometer wavelengths as well, which will also be the topic of this talk. Active Fiber Systems has been founded in 2009, and its success mainly relies on the rapid transition from research into reliable commercial systems. The main market is the research field, and Active Fiber Systems has evolved now to one of the technological leaders for high-power ultrafast fiber lasers. The concept behind pretty much all lasers from Active Fiber Systems is the actively doped optical fiber. And fiber amplifiers are known to be very reliable, simple, and most importantly, they provide excellent beam quality. However, they have one quite big disadvantage. Their power scaling is typically limited by nonlinear effects. And there are two main strategies to mitigate nonlinear effects in ultrafast fiber lasers that both aim at reducing the peak intensity in the fiber core. The first is the use of short length, large core fibers that still emit near diffraction limited beam quality. And the second is the well-known concept of chirp pulse amplification, short CPA, an invention that you all probably know has just recently received the Nobel Prize. Now, the third concept that is quite important for power scaling of our systems is the coherent combination of multiple amplifiers. The concept is quite simple. You start with one front end, and then you divide the seed beam to different channels. And each individual channel contains an amplifier, and the amplified beams in the end are recombined to a single beam. So this coherent addition is based on constructive interference. So you have an interferometer of different channels, which means you need to stabilize the path length that the light travels or the pulses travel through each individual channel. This can be done by a certain phase control mechanism in each individual channel. So now you might ask the question, so what do we have to change in order to go from 1 micrometer wavelengths to 2 micrometer wavelengths? And the difference is mainly going from ytterbium as the active dopant to thulium. Thulium has some advantages, obviously the emission wavelengths, but also some disadvantages, which is the reason why thulium-doped fiber lasers have been a laboratory curiosity for quite some time now. The properties of thulium are a very broad amplification bandwidth, which is sufficient for the amplification of sub-100 femtosecond pulses. At the same time, we typically have a quite large quantum defect due to the pumping at 790 nanometers. So we typically have strong quantum defect heating during the amplification process. Fortunately, there's a process called cross-relaxation, where the relaxation of one ion can lead to the simultaneous excitation of a neighboring ion, which effectively doubles the quantum efficiency. And it has been shown that the efficiency by pumping at 790 nanometers of thulium-doped fiber amplifiers can be scaled to more than 70%. So there are also some technical challenges, like the availability of suitable high power optics and also the availability of high brightness laser diodes for optical pumping. As I've already mentioned, the cross-relaxation process is not always achieved. So you need efficiency optimized fibers, which is a chemical optimization of the fiber design, but you also need to follow some rules concerning the experimental guidelines or the way you seat and cool your fiber amplifier. And there's also a problem due to the longer wavelengths. We overlap with the atmospheric absorption of humidity or water vapor, and this can lead to a degradation of the beam quality as well as a degradation of ultra-fast pulses. And this can significantly hamper the performance and also the power scaling of ultra-fast thulium-doped fiber lasers. So this, of course, can be overcome by using vacuum chambers. This brings me to the concept and setup of our current laser system that I'm talking about here. So we start with an oscillator emitting at around 2 micrometer wavelengths, providing ultra-fast pulses. These pulses are stretched and picked down in pulse repetition frequency and in an all-fiber format and pre-amplified. These pre-amplified pulses are then sent and divided into 4 different channels, which each consist of main amplifiers. And in those main amplifiers, we have quite some amplification and to high pulse energies. And then we recombine the pulses from each individual channel and compress them to a final pulse energy of 240 microjoules at 500 kilohertz pulse repetition frequency and an average power of 120 watts. And as you will see later on, we reach pulse durations well below 120 femtoseconds. You can see in the setup, all the green boxes are vacuum chambers. So all the channels and the high power beam passes are contained in vacuum. So let me give some more details about our all-fiber preamplifier. It includes an acousto-optical modulator for pulse picking. So we can tune the pulse repetition frequency between 25 kilohertz and 25 megahertz. The seed system provides a spectral bandwidth of more than 100 nanometers, centered at 1940 nanometers, and provides a Fourier limit of around 110 femtoseconds. The stretch pulse duration after pulse stretching is 700 picosecond. We have 4 main amplifier channels in the system, which are based on a thulium photonic crystal fiber. This fiber has been operated up to 130 watts in each individual channel with more than 50% slope efficiency. As you can see, so we have some positive contribution of cross-relaxation and excellent long-term stability in those modules due to an advanced cooling concept. So in our compressor, we used highly reflective dielectric gratings, which enabled a compressor efficiency of more than 89%. And due to the polarization maintaining property of the main amplifier fiber, we have a polarization extinction ratio of more than 20 dB in each main amplifier, which allows us to achieve a very high combining efficiency of more than 95%. As you can see, which we also confirmed, that we have excellent beam quality with an m² as small as 1.1, even at the highest average power of 120 watts. Here you see the compressed pulses at a pulse energy of more than 200 microjoules, which corresponds to 120 watt of average power at 500 kilohertz. And you can see that we reached a pulse duration of less than 120 femtoseconds. So assuming that more than 75% of the energy are contained in the main feature of the pulse, this corresponds to more than 1.3 gigawatt of peak power. All this at a center wavelength of 1940 nanometers, as you can also see on the right graph here. We also performed a long-term test over 90 hours. You can see that the system was very stable over several days, not only in the power, but also in the beam pointing. So this is an excellent prerequisite for nonlinear pulse compression to the fuse cycle regime. And those lasers have been used in the past, for example, for the generation of mid-IR through difference frequency generation, as you can see here, or you can actually go for high harmonic generation towards the water window, as is shown here in this graph, and has been recently achieved in the group in Jena at the Institute of Applied Physics. And of course, once you reach the water window, you can do very interesting experiments like coherent diffractive imaging. And this being said, I would like to point out that we are not at the end of power scaling those thulium-doped fiber lasers. Based on this concept and by adapting the fiber design, we might achieve 3 millijoules and up to 300 watt of average power with a pulse duration of less than 150 femtoseconds. And also you can add several more channels, and this can linearly scale the output performance of those systems. So we believe that this is a great alternative to 1 micrometer systems that are often used to pump OPAs that emit at around 2 micrometer wavelengths. So give me a quick outlook. So based on the current system design with 4 channels and this fiber type, we can still scale up the pulse energy to more than 500 microjoules. And we believe that we can reach more than 200 watts with this current system. By going to different fiber design and adding more channels, we can actually scale up the pulse energy to more than 3 millijoules. And of course, at slightly lower pulse energy, however, we should be able to reach more than 1 kilowatt of average power from those combining systems in the near future. At the same time, we are still in the process of developing fuse cycle generation from those systems, for example, based on anti-resonant hollow core fibers, aiming for less than 20 femtosecond pulse duration at more than 100 watts of average power. With this, I would like to thank you for your attention, and I hope I can answer all the questions that you might have.